start his presentation.
This meeting is being recorded.
So over to Parth for your presentation on Diplexers.
Good morning, everyone. So I will just start my slideshow here. After we reach a certain step in the slideshow, we will continue towards our CAD program, where we will discuss some things about PCB design and design considerations taken in place while designing RF PCBs. So let's just start with the slideshow.
Parth, go in full view slideshow. Yeah, perfect. Please go ahead. No interruptions now.
Okay. VHF and UHF diplexers. So as you can see, this is the end PCB that we designed. The name of this particular design I have kept the cat and the dog, because I thought the low pass and the high pass filters look like a cat and a dog. So that's a fun thing. So let's start with the obvious questions. What are diplexers? Diplexers is basically a low pass filter and a high pass filter, which is arranged such that the frequencies go to a separate line without interfering with each other and without messing up the SWR of each other. If you had just connected two coax in T configuration without any filters, it would mess up your SWR very bad. So that's how that's where we need diplexers. So it allows one frequency signals to go via one way and the other frequency signals to go via other way without causing much harm to the radio itself. So as you can see, you can use two antennas to a multi-band radio like a Baofeng, which has both the bands VHF and UHF. And you can use two antennas such as a VHF Yagi and a UHF Yagi, or you can use bazooka antenna and a ground plane antenna for VHF, because for you maybe the UHF repeater is far closer and VHF is far longer. So you may want a Yagi or a ground plane for triggering VHF repeater and have a normal antenna for a UHF repeater. Also, it can work both ways. So you may have a single multi-band antenna with two dual band radios, with two single band radios. So it's like you have a very good multi-band antenna, and you have a very good radio, but that radio works on only a single band. So you can use that radio with the dual band antenna, and you can use other band radio also with the dual band antenna at the same time. So the first question due to VPR asked me that in his times duplexers were very expensive. It would cost lakhs and it were very bulky. So let me clear the confusion. The thing that VU2 VPR was talking about was he was talking about a duplexer. Duplexers and diplexers are basically the same things, but we have standardized this, normalized these terms. Duplexer for a duplexer diplexer that is working in a single band. So like you are splitting two frequencies in the VHF band itself. And diplexer is like split VHF and UHF band differently, like 10-meter band and 2-meter band, 20-meter band. You separate them. That is the work of a diplexer. And duplexer is like 2-meter, two frequencies in the same band. Duplexers need to have a sharper curve, and to obtain this very sharp curve, you have to use the help of waveguides or cavities. You say, let me just show you the diplexer. So you can look. This is a duplexer. You can like see that the high pass filter is made up of many cavities and waveguides, and the low pass filter is made of very many cavities and waveguides. This is the work of a duplexer. Now you can use. We are actually using duplexers in our repeaters. Like for example, you have a dual band ground plane antenna. You use a duplexer to separate the RX and the TX frequencies of that antenna, and use separate radios for that. This is duplexer is required in a repeater configuration. A repeater configuration of terrestrial signals, which are in the single band. For satellite repeaters, you know that satellite receives at VHF and transmit UHF back. So that is something you need a diplexer for. You need a diplexer for satellites as well as for terrestrial use, and duplexer is mostly used in terrestrial repeater use. Let's get into the designing part of the diplexer. So as I said earlier, that a diplexer consists of a low pass filter and a high pass filter connected to the two different lines. The problem here, there is you seem to like there is no problem at all, except that sometimes the low pass filter is not very merciful on the high pass filter, and those two things cannot go together. You can have such things happening, but sometimes it just works, and sometimes it is not that easy. And you also have to take certain things into consideration about the board layout. You need to have the components very close together. We will talk about that later in the PCB design case. And then that's all. You need a low pass filter and a high pass filter, and there you go, you have a diplexer. But getting the values right and getting tuning it so that the insertion loss is low is something that takes time. So step one, we have to Chebyshev filters exist, and those are how they exist is they exist in the form of normalized element values. So like for a Chebyshev equal order of 5, and if I want the ripple to be 0.5 decibels, I will have a fixed values for these components. So L1 will be always 1.8068. Also note that this is for resistance 1 ohm, and we have to scale it later into a larger, greater frequency. So these are called the normalized values for a filter. This is for a low pass filter. Normalized values exist for low pass 1 ohm filter, and the inspiration from this project was K1 AG, who used Handbook of Filter Synthesis by a Russian engineer, who he has put all those good filter designs, normalized value in a table. But there are two different set of values we get if we Google the same exact thing. So maybe this is far more tuned, or this is less tuned. Maybe it can happen that you get in this tough. It's a tough choice to make between what you want to choose. Like, okay. Apart from that, we have to make diplexers of all these, and by testing and analysis of the circuit, we can determine which one is the better. So as I am following KI0AG, so I will just stick with his values. After, but as I said earlier, those values were for 1 ohm, and normalized values have to be scaled to the new values. So there are formulas for this thing. As you can see on the screen, these are the formulas. Capacitors, for the capacitance, you have to divide the old capacitance by the impedance you want, and then multiply it by 2 pi f. And for the inductance, you have to multiply the normalized inductance by the impedance and then divide it by 2 pi f, right? So by doing this on a Excel spreadsheet, we get these. Now, getting custom components is very hard and it's expensive. So we will just round them up to the nearest standard component values. Now what we have just obtained is the low pass filter side of this diplexer. Let me just check if I skipped a point. Yeah. So you can have your values for your own characteristics. You can have a 0.01 decibel ripple or many such. This table exists. So if you want a capacitor input, just take this. Take the first values as capacitance. If you want the inductor input, take the capacitance values as inductor values. This is in farads, and capacitance values are in farads, and this is in henries. So this is not a very nice unit to work with, because you know those are very large unit for a capacitor and an inductor. We just, yeah. So you have to scale them up, and then you will get values which are in nanohenries and picofarads, which is much more convenient to work with. You can get these in standard SMD packets. And we just repeat what we did for the high pass filter side. To get the high pass filters normalized values, we just take the low pass filters normalized values and inverse them. High pass filter is typically capacitor input, so you will just switch the capacitor to the inductor, and using the same formulas you get the following values, which are also in picofarads and nanohenries. This is how the schematic should look like a common RF line which goes into a low pass filter and to a high pass filter, which will give you 2 meter and 70 centimeter respectively. Yeah, I have not multiplied this by 220. I have multiplied this by 220 megahertz. So the cutoff for a low pass filter is 220 megahertz, and cutoff for the high pass filter is 380 megahertz. That's yeah. So we will get to the PCB design part now. This is the most fun part of this. This is the fun part of the whole presentation. If you guys have any doubt in the formula parts, you can ask it now or later.
Everything at the end of presentation.
Okay. So I will switch my sharing to KiCad, and here are the key things you want to look for. You want to know how KiCad functions. You want to know how to calculate the trace width for the impedance matching. I will just give a short introduction to net class and nets. There is a 3D viewer embedded into KiCad. There is also a SPICE program in KiCad. You can panelize PCBs in KiCad using a plugin. I will show that, and how to contact the PCB manufacturers by their website. I will just talk about that in this part. Yeah. So you can see this is our schematic in KiCad. KiCad has two functions. First, it has a schematic editor, and second, it has a PCB design tool. So you can assign the footprints of PCB design into the schematic, and you can assign the schematic symbols from the PCB design. This is much convenient for use by hobbyists, and KiCad is also free to use, unlike other softwares, which makes it very affordable and attractive options for hobbies use. We will just go into the simulation part of it. If you go into inspect tab of the no, let me just show you how to add footprints and all. So this is called as the add footprint button. Here you can get all those symbols that you see of the coax, capacitors, inductors. You can get this in the add symbols button, and the ground plane and the RF lines can be classified net by the net markers, which are these right here. This will automatically translate to your PCB design tool. You will automatically get the nets, ground, and your RF into your PCB design tool if you do these things correctly, which is like a professional side of a hobbyist. So it's not responding. I will show you a full suite of designing filters and simulating them in this session, and then we will move on to the PCB design. So whenever you design a filter or any RF circuit, you first have to simulate it if it works correctly. The normalized value you see, we had a problem with those normalized values. Somewhere the internet was telling one thing and the Fuji was telling other thing. So in such cases, it's better to inspect and take the simulation and check which one is the so KiCad has an inbuilt SPICE simulation tool. To you can wait. KiCad has an inbuilt spice simulator tool, but I cannot get it to work right now. I'll just show you another spice simulation tool, which is called as RF-Sim 99. It is also great for hobbies. I have both the Diplexer designs right here, which are corresponding to the KW1 KWI0AG and the internet part. It is also designed by with the help of a tool called LC. LC also has the same normalized values as the internet, but this has a slight SWR difference of 0.2 in compared to this. Like you will have a SWR greater of greater by 0.2 than compared to this. Like this is 1.2 for 144, and this is 1.4 for 144 megahertz. So I'll just you just have to place all the components, place the ports. The other end must be terminated with a 50 ohm resistor to simulate a dummy load. And as you can see, here's our profile of the Diplexer. So as you can see, our Diplexer will start to decrease from 200 megahertz around, and it will, like, it is designed for 280 megahertz, but you know, or it's not actually a very steep decline actually. And the what a Diplexer should have is symmetry. So one band should not be attenuated more than the other band. If you don't want that thing, if you want that thing, I don't know. A Diplexer should also have symmetry in components. So this inductor and this inductor should be close to the same value. As we see in the internet normalized chart, these two are not the same value, which will create some problems in manufacturing and assembling these components. Also, it will make an uneven distribution, which is not the case right here. So this is for the 144 megahertz, and I will just switch the places of the port. And now it shifts the pass band to 144 to the VHF band. As you can see, from 426, your amateur band is near about at this place. So it's slightly attenuating the UHF band, but not the VHF band. To do the power, to check the power of this thing, suppose you have a capacitor right here, which is rated for 50 volts, and this is rated for 50 volts, then the middle capacitor should always be rated for more than the double of these two. So if this is 50 volts, this should be 100 volts. That's the, like, this capacitor and this inductor, these two define the power that is passed through this system. If I take a circuit analysis tool and check, this will have a lower, this will have half the voltage, near about half the voltage that is of this the middle component, which is what I found by experimenting with the circuit analysis tool. This is why I never recommend anyone to go beyond 25 watts, because 25 watts is like 25 volts RMS, which is a double of 25 volts is 50 volts. So my capacitors are rated for 50 volts. So that defines my power, that is 25 watts. The middle capacitor and the middle inductors define the power for your circuit. Now we will go back into KiCad. So you can just move around this. Let's go to the other fun part, that is PCB design. It will take us some time to load. Okay. Yeah. There we go. This is the design of our Diplexer. So let's just try to replicate this design which we have done. So there is a really awesome tool called library loader, which is created by the component source engine, which automatically loads your footprints into KiCad or any other CAD software, which is how it helps me a lot. The only thing I don't trust the default footprints in KiCad, because you may know that a problem arises with this particular footprint right here. This was supposed to be a SMA edge mount, but it was a standard SMA edge mount and not the smaller size which we all use in our electronics. So getting this part is the PCB footprint is right, but getting the part is very difficult. In and also we have chip shortage. So here is your Diplexer. This you can see there are layers on your right side in the appearance tab, where you can toggle the appearance of these layers. You can also switch between layers and do these things. So first thing we want to do is get out of the PCB design software, get into the calculator tools that KiCad provides. And right here we have in this tab transline, we can see transmission line type. So what we want is a coplanar waveguide with ground plane. You can see those images, illustrations which you want. The type of transmission line you want, you can just look here. For our project, we have a ground plane, and it also has a coplanar ground plane. So for our PCB, we are using FR4, so that will be epsilon r will be 4.6, tan omega will be 0.02, and all those things are basically the same. You can actually you can decide the stack up of how you want your PCB in another calculator, which is in the PCB design tool. You can determine that. And so if I want power, which is rack width, if I want a power current of 1 ampere, and delta D is only, okay, we can do all these things. And then default trace thickness and the one support, one which is considered standard by many PCB manufacturers is 0.035 millimeters, which is the standard for trace thickness. And we can just calculate what we want from here. So trace width is 0.45. We want our trace width to be greater than this number to allow 1 amp of current to pass through. We can just then, to be on the safe side, I have put the width equal to 1 millimeters, and we can. So if I don't know the spacing, I can click on this radio button right here, and I can synthesize. If I want 50 ohms, I can synthesize. Yeah, that's very. Synthesizing can be a bit difficult. So yeah, by your spacing you can calculate width, or by your width you can calculate your spacing given the distance between the ground plane and the microstrip. Also, there are many online calculators to do this specific thing. I don't know why it is doing such thing. This should not be the case. Analyze which is going and typically you want your spacing to be 0.2, so you can calculate your width using this. Or you can just copy paste the dimensions from a PCB that you know has 50 ohms impedance. Okay, so that's done. We'll just create a small area to work with right here. Okay. It's, yeah. And so these are called vias, which pass through the board into the bottom layer. So these pass through the board by this. These are like columns which you can use to make contact, electrical contact between the two layers of your board. So like the bottom ground plane of this and the top ground plane are connected with many wires. Those are called as stitching wires, as you see here. These have two functions. First, it maintains the physical strength of the PCB board, which so like you cannot pull the two layers apart if you have many wires between them. Two, it allows thermoregulation, like it will dissipate all the heat that is on the front side of the PCB to the back side. So it also helps in thermal dissipation, and it blocks the RF any radio frequency interference. It's like acts as a Faraday cage. You can make a Faraday cage on the PCB by using wires. These are called as stitching wires. So wherever you think there is a ground connection, you can make a wires. This reduces the path distance traveled by the ground electrons, which in turn makes your impedance very good. Okay, this is like for example, you want to make a trace which goes from here to here, and once you make this, you want to make it the same trace width and or you want this particular net, which is RFN, to be the same width and have the same clearance as the impedance we calculated before. So we go into the nets tab in appearance. You can see we have two nets, which is RF and ground, and there are net classes. Net classes are basically a greater set of nets which have the properties trace width and clearance assigned to them. Yeah. So yeah, as we calculated before, if we want 0.219 m of clearance, we'll go with like 1.00 millimeters of track width. You can assign this net class to our traces. And it will have it wants to join the RF in, because that's the net it is in. So we will just not make it. That's how you do it basically. Clearance is 0.19 from net class RF. Other thing I talked about is panelizing the PCBs. So for panelizing them, just spy is done. 9 पासून नंतर कधी देता येते, कधी देता येते. Analyzing PCBs, yes, analyzing is the one left. So we'll just close that one and make a new PCB right here. Okay, yeah. You want to get the standalone application for this. Make a new PCB with the standalone PCB editor. And here I have installed a plugin which is called as KickIt. This is the one which will panelize our PCB. So I can put my input file right here. I'll just slide through all those things. How many rows you want, how many columns you want, the rotation if there is any, alternation if you want. This is okay. I'll just get it rows. I want 2 rows. I want 2 columns. I want 2 millimeter space between them. Millimeter is what most PCB manufacturers have their drill size set to, which will save you a lot of time and money. So we come to the section which is cuts. Cuts is what type of tabs you want in between those PCBs, which will keep them joined during the manufacturing and which we can break when you want to pack them up, you want to separate them. So there are 2 main types of which are considered standard. One is the mouse bites and other is the V cuts. Both have their own benefits. Mouse bites are a bit expensive, but they are more generally used than V cuts. V cuts are made by a knife-like thing that the CNC machine will cut your pieces into. They tend to go in a straight line, so you cannot make a lot of absurd shapes using V cuts. You have to the whole board will get cut into if you use V cuts. And mouse bites are let me just show you what mouse bites are. Just this is very oof. Yeah, these are what mouse bites are. They're like tabs in between, and the tabs have holes in them, which you can easily break just by your hands. Let me show you the 3D viewer. So all the footprints in your design will have their own 3D model assigned to them, which you can change in the footprints tab. And this is how our boards look like when they are panelized. Panelizing is what you do when you want to make it's cheaper than to buy those in single units, because the PCB manufacturer also panelizes them, and when panelizes them with other clients, and they take more money for panelizing it themselves, because they are using their intellectual power and labor in that. So this will help reduce your cost if you panelize them by yourself. Now I have the PCBs, I have the components. How do I solder them? So in India, it is very difficult to get in anywhere actually. It is very difficult to get a PCB reflow heater or a hot bed or a oven. So what I did is take a pan put it on a gas stove, put salt or sand on top of it. If you use sand, you don't need to use aluminum foil. Aluminum foil is what protects the PCB from the because salt is actually corrosive, which I learned in the temporary group chat and by experimenting myself. So you want a piece of aluminum foil if you are using salt, or you don't need it if you are using sand. And if you want to make it more even, you can add an oven attachment, which is just any bowl or a kadai. So this is how I soldered them. Uses for Diplexer, satellite communications. I said that satellites transmit and receive at different bands in the VHF UHF range. So you need a Diplexer for that. Also, in satellite mode of communication, you need 2 radios and a dual band Yagi. You need the second radio to hear yourself. That is how you know that you are getting a satellite contact and not just random. You are just randomly aiming at the sky. It's just like you are hearing the repeater tail, but you are hearing yourself. It also eliminates the need of 2 separate coax cables and antenna selectors for dual band antennas. You don't need an antenna selector or a coax cable for dual band antennas. No more with this. You can just use a single coax cable with a Diplexer, which will get you 2 radios connected to a single antenna, which is how repeaters are made. Also allows creation of dual band antennas. You have 2 different band antennas, slap on a Diplexer, and you have a dual band antennas. And you can see this is the arrow antenna Diplexer, which the Arrow company, you might have known the Arrow antennas. They have this Diplexer inside, but this thing is, they have monopoly over this thing. They charge you like 10,000 rupees for this. And this is how your satellite rig is made. You have a VHF Yagi and a UHF Yagi, which and it also reduces your need for drilling 2 holes in your walls just for 2 different bands. That's it for the presentation. Any questions?
Yeah, now the platform is open for Q&A. We have hardly 10 minutes now. First, identify yourself and then ask question. Looks, I think everything is understood, or it has gone over the head. No questions? Please raise your queries. That makes the subject interesting. Yeah, please ask the question. Hello.
Sir, good morning. Rajesh Sarvajna this side.
Yeah, Rajesh, go ahead. Please go ahead.
Yeah.
Please go ahead, Rajesh.
Sir, I want to ask a question. Any application in the industry?
Can you please repeat?
Can we use some application, similar kind of application in the industry for, so for communication or something like that?
In the industry, are there any applications for diplexers? Is that what
Yes.
you are asking?
Yeah.
Yeah, as I said, those are used in satellites.
Okay.
Satellites tend to avoid superhit radios, so they just use a Baofeng type approach, making a chip on a radio on a chip, which covers both the bands, dual bands. So you need and satellites, you know that they have two different antennas for VHF and UHF as a just as we have. So they also need a diplexer right there, up there, to divide those two frequencies. And it is also used in general case scenarios like TV radio stations to use two different bands sometimes in communications. It is used in industry.
That's what the question was actually. What will be the application, say, maybe for communication within the industries?
Rajesh, it is already used in industry wherever there is a communication on two different bands. So it's a commercial product also available in the market. But
Yeah.
of course, this particular project is applicable only in the communication industry. I hope the answer is clear.
Okay.
Okay, next question, please. Looks everything is clear. So friends, we have come to an end, and this is 9:24, and Parth has given a very good outlook about the diplexers, and you all must have learned the design of the printed circuit board in such filters is very, very crucial and critical, because you are playing with the high frequencies. So there could be many problems. So you have to use the tools which are available and which are available freely for the hams and experimenters. So use those tools. Probably you can also become an expert designing the diplexers, duplexers of your requirement in the ham radio. Rajesh, this particular lecture was focused on the ham radio, a hobby. But of course, it has got applications in industry also. And as rightly said by Parth, the Arrow is the company which is making such antennas and duplexers inbuilt. Such duplexers are also available in our mobile phones. Everywhere, when you operate the split frequency, it is used. When you have a low difference between the transmit and receive frequency, that as we use in VHF, just a 600 kilohertz difference, it's very difficult to develop such diplexers on PCB. Then you have to go for the cavity resonators, which is rightly used by most of the ham clubs for their VHF repeaters. So anyway, Parth, you have explained it very nicely. You have also explained the PCB design part of this project. Understand, you have made the PCBs, they are available. So those who are interested can directly contact Parth. Number and contact details I already shared in the various mails, so that you will be able to make the project a great success. So thanks a lot everyone for attending. Let us meet next month for another exciting project. First Sunday of the month we normally meet, and we will hear from someone about another exciting story about such projects. Those who are attending want to and wish to give presentations, they are most welcome. Please get in touch with me. Pune Hams, we organize such tech talks every month. We also have outings also. So 17th and 18th June, we have planned a field day very close to the Panchet Dam. Those shortwave listeners and hams are interested, get in touch with me. It's an overnight stay. We may also go for a stargazing in the night, because it's a dark sky. Pune hams, we have two repeaters, VHF as well as UHF. The frequencies are given, and they are quite popular. The Echolink, which is connected to VHF, is most popular, conducted by Dilip Bapat, as well as VU3 Yankee Echo Juliet, Oldman Kunal Gautam. and they have kept the flame running for the hobby. It's a good effort by Pune Hams, I must say. Thanks a lot, everybody, for attending. Let's meet next month. Have a wonderful day. Bye-bye.
Yes, thank you, sir. Thank you. Thank you, Parth.
Thank you, everyone.